The latest images captured by the James Webb Space Telescope have astonished scientists, providing insights into the universe that were previously unimaginable. Rather than simply expanding our comprehension of the cosmos, these images have revealed a puzzling reality, suggesting that our current understanding is insufficient to fully comprehend the early stages of the universe's existence. The established theories concerning the origins of the universe now seem to be stretching their limits, prompting the need to investigate alternative hypotheses about its formation. This raises the crucial question: how did the universe come into being, and why are these discoveries posing challenges even for the most experienced experts in the field of space science? It calls for a deeper investigation into the true nature of the Big Bang and its ever-evolving complexities. It may now be time to reconsider the Big Bang theory itself, as the public's perception of it has often been oversimplified. The Big Bang was not just an explosion within pre-existing space. Rather, it marked the very creation of space itself, unfolding approximately 13.8 billion years ago alongside matter and time. A core idea in modern science and cosmology is the concept of a singularity, a point where gravity becomes so intense that the curvature of spacetime becomes infinite. After billions of years since the universe's birth, we now realize that our cosmic home is part of a vast collaboration. For scientists, this discovery represents a vital aspect of the universe's existence, showcasing its ongoing expansion. The universe doesn't merely drift into existing space. Space itself is still expanding, contrary to traditional theories that suggested otherwise. It is believed that the first stars began to shine roughly 200 to 300 million years after the Big Bang, marking the end of the so-called dark age of the universe, when the first bright celestial objects formed and evolved into galaxies. However, the speed at which these galaxies developed remains a mystery. A major breakthrough occurred on July 22, when the James Webb Space Telescope released its first images, revealing several galaxies, some of which were already in existence about 300 million years after the universe's creation. While younger than the galaxies we see today, these early galaxies were smaller and less massive, in line with the scientific models at the time. In the early universe, the matter density was too low to form galaxies as large as those we observe in the present era. This discovery began with the detection of 6 notable redshifted bright spots by the James Webb Telescope, igniting one of the most significant cosmic puzzles in recent years. These newly discovered galaxies, though comparable in age to previously identified galaxies, appeared almost as large as our Milky Way. This finding has intrigued researchers in the field of Big Bang cosmology. When scientists analyzed a series of images taken by the telescope's near-infrared camera, they confirmed the existence of these distant objects. They used redshift data to determine that the light from these galaxies had traveled over 1 billion years before reaching Earth. This suggests that these galaxies existed between 570 and 700 million years after the confirmed Big Bang. This remarkable discovery challenges traditional cosmological expectations, which had predicted the formation of much smaller, less evolved galaxies at this stage of the universe's history. Instead, the James Webb Telescope revealed galaxies nearly as large as the Milky Way, defying these predictions. The gravitationally bound stars in these galaxies had already accumulated mass surpassing 10 billion times that of the Sun. One of these galaxies even seemed to possess a mass greater than 10 billion solar masses. However, whether this hypothesis is entirely accurate is still open to debate. Even if these findings are correct, the mass in the early universe would be far greater than anticipated, creating an even more complex puzzle. The discovery of these galaxies poses a significant challenge to nearly all traditional cosmological theories. Even if one of these galaxies proves to be accurate, it would force us to re-examine our assumptions about the existence of these early cosmic structures. The matter density in the early universe would need to be far greater than initially assumed. Another potential explanation is that these galaxies may have formed in ways entirely unknown to us. These discoveries are raising questions that demand a reassessment of the Big Bang theory. Many space scientists are frustrated by these revelations, and their concerns are frequently expressed in scientific publications. Those who challenge the prevailing theories are often labeled as unorthodox or extreme. However, it is evident that even those who continue to support the Big Bang theory face unresolved questions. Among these is the fundamental issue of how 13.8 billion years ago, something could emerge from nothing. Could something truly come from nothing, or was there a catalyst for this event? Did it occur randomly? Stephen Hawking famously pointed out that the nature of time, as we understand it, began with the Big Bang. Therefore, this process could not have been initiated by something else or triggered by an external cause. Similar doubts arise concerning the uniformity of radiation and matter throughout the universe. Regardless of where we look, or at what distance we observe, we see a similar distribution of systems, nebulae, and radiation across the cosmos. Modern scholars explain this phenomenon with the theory of cosmic inflation. However, other experts have expanded on this theory, suggesting that the universe expanded in a turbulent manner. According to this model, expansion occurred only in localized regions like bubbles, while other areas continued to expand without end. This model raises the intriguing possibility that other universes may exist within these expanding bubbles, each governed by its own set of physical laws. Such a perspective implies that our universe may not represent the totality of existence, but rather be part of a larger and more intricate structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe is proposed. However, this is just one of many theories in cosmology. For instance, an article published in NASA's Big Time magazine in 1955 suggested that the universe may have never had a Big Bang and could have always existed, possibly for an infinite period. In this interpretation, the expansion of the universe would be absent, with the continuous evolution of matter giving the impression of gradual development over time. One particularly captivating hypothesis arises from quantum physics and string theory. Some experiments have hinted that our entire universe could be a projection or simulation from a higher dimensional reality. While this might sound like the premise of a science fiction story, it connects to the Kardashev scale, which measures a civilization's ability to harness the energy of an entire galaxy. A Type 3 civilization, capable of utilizing the energy of a galaxy, might be able to create an ideal simulation of a universe. However, proving the validity of such a scenario remains a daunting challenge. Exploring the depths of cosmology and the origins of the universe brings us into a realm of great mystery and ongoing scientific investigation. The new images from the James Webb Space Telescope have reignited debates about the very fabric of existence, putting established theories to the test and urging scientists to reassess core principles of our understanding of the cosmos. Central to this discussion is the theory of the universe's origin, which forms the foundation of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from a dense, hot state, rapidly expanding and giving rise to the space-time and matter we observe today. This immense event wasn't merely an explosion in pre-existing space, but also signaled the beginning of space itself. The concept of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, helps support our understanding of the early universe. However, the discovery of large, mature galaxies just a few hundred million years after the Big Bang challenges traditional ideas about how quickly the first structures formed. These discoveries suggest that the early universe had a far higher density of matter than previously thought, raising questions about how such large structures could have developed so quickly. This compels cosmologists to rethink how galaxies like those observed by the James Webb Telescope could have formed so early in the universe's history. One key theory impacted by these findings is cosmic inflation, which posits that the universe expanded exponentially in the moments following the Big Bang. This rapid inflation is thought to explain the uniformity of the cosmic microwave background radiation we see across the universe today. However, new discoveries are introducing complications that may require adjustments to our understanding of inflation. The formation of these massive early galaxies also raises important questions about dark matter and dark energy, two mysterious components that constitute most of the universe's mass and energy. Although dark matter is believed to provide the gravitational framework for galaxies to form, scientists still lack a clear understanding of its distribution and properties in the early universe. In response to these unresolved mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang theory. Some of these ideas suggest that our universe could be one of many in a vast multiverse, each with its own set of physical laws and constants. These concepts, stemming from string theory and quantum cosmology, propose a far more intricate and interconnected cosmos than previously imagined. One increasingly popular theory is that of time inflation, in which universes continuously emerge within a larger expanding space. This suggests that our universe might be one bubble among many, each with distinct physical properties. The challenge, however, is finding observational evidence to support these speculative ideas, as they push the boundaries of what can be tested scientifically. Another provocative theory posits that our universe could be a computer-generated simulation, drawing parallels to advancements in artificial intelligence and computational science, where simulations can recreate complex systems. If true, this theory would radically change our understanding of reality and prompt profound philosophical and scientific questions about the nature of existence itself. As observational astronomy continues to advance, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to reveal even more secrets of the universe. Future observations may provide deep insights into the earliest moments of the cosmos, potentially offering clues about its ultimate fate and the fundamental principles that drive its ongoing evolution. Meanwhile, particle physicists remain committed to uncovering the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal in theoretical physics. In the realm of quantum mechanics, debates about the nature of time persist, with some theories proposing that time itself may be evolving or even changing at the most fundamental levels. Understanding the nature of time in the context of cosmology could revolutionize our understanding of the universe's origins and its ongoing development. Furthermore, the search for extraterrestrial life continues to fuel both public curiosity and scientific investigation. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments beyond Earth. Future missions, such as the James Webb Space Telescope's analysis of exoplanet atmospheres, could uncover biosignatures that point to life beyond our planet. As scientific exploration progresses, so too does the philosophical inquiry into humanity's place in the universe. The search for answers to questions about existence, the potential for intelligent life elsewhere, and humanity's future in space exploration will continue to shape discussions across both scientific and philosophical realms. As we continue to push the boundaries of scientific exploration, we find ourselves at the intersection of new discoveries and long-established theories that are being challenged. The growing body of data from instruments like the James Webb Space Telescope is beginning to reveal a universe far more complex than previously imagined. Each new revelation forces us to confront the limitations of our current understanding and compels us to reconsider fundamental concepts, from the origins of the cosmos to the very nature of existence. These new images are not just adding layers to our existing knowledge. They are reshaping our approach to fundamental questions that have plagued scientists for centuries. The images from the James Webb Space Telescope have ignited widespread discussion, particularly concerning the formation of galaxies in the early universe. The question of how galaxies could form so quickly after the Big Bang is one of the most pressing issues now facing cosmologists. The early universe, as depicted by current models, should have been much less capable of producing large, mature galaxies so soon after its inception. Yet these new findings suggest that the formation of large galaxies might have occurred at a much faster rate than previously believed. One of the critical issues raised by these discoveries is the nature of cosmic inflation, a concept that has been central to our understanding of the early universe. According to this theory, the universe underwent an extremely rapid expansion in the moments following the Big Bang. This expansion is thought to have explained the uniformity of the cosmos and the smooth distribution of matter that we see today. However, the detection of large, developed galaxies at such an early stage challenges the idea that the universe expanded uniformly across all regions. This discrepancy suggests that there may be much more complexity in the early universe than current models can account for. As scientists continue to analyze the data from the James Webb Space Telescope, they are also beginning to reconsider the role of dark matter and dark energy in the formation of these early galaxies. Dark matter, which is thought to be responsible for the gravitational pull that holds galaxies together, has long been a subject of mystery. Its exact properties and distribution in the early universe remain elusive, and these new findings could provide the key to unlocking some of these unanswered questions. Dark energy, which is believed to drive the accelerated expansion of the universe, is another factor that scientists are now beginning to explore more thoroughly in light of these recent discoveries. The implications of these new findings extend far beyond our understanding of galaxy formation. They challenge the very structure of our cosmological models and force us to ask bigger questions about the universe itself. How did the universe transition from the chaotic, dense state of the Big Bang to the more organized structures we see today? What role did dark matter and dark energy play in this transformation? And most importantly, what do these discoveries tell us about the future of the cosmos? The recent revelations also bring into question the long-held assumption that the Big Bang was the singular event from which everything emerged. Many scientists, particularly those who support alternative cosmological models, have long believed that the Big Bang is just one phase in an ongoing cycle of creation and destruction. These models, which often involve the concept of a multiverse, suggest that our universe could be one of many, each with its own unique set of physical laws. If this is the case, it would mean that our understanding of the universe is far too narrow, and that we need to rethink not only the Big Bang but also the very nature of reality itself. One of the more radical ideas that has emerged from this reevaluation of cosmological theory is the possibility that our entire universe could be part of a much larger and more complex structure, one that transcends the boundaries of space and time as we understand them. Some scientists have proposed that the universe could be part of an eternal cycle of birth and death, where each cycle gives rise to a new universe with its own set of laws and constants. This idea, often referred to as timeless inflation, suggests that universes are continually emerging within a larger, ever-expanding space.